All right, cool. We made it back. Main things coming up is quiz 1. Hopefully that one is like getting done or planned to get done. So sometime tonight. If you're not going to do it like tonight, then at least like put a note in there and give us a new deadline like in the next couple of days. Project 1 we were talking about on Friday, and we were just talking about like up front a little bit of, hey, is this okay, or what were you looking for here? Were there leftover questions? Like, I didn't talk to everybody on Friday, but was there anything burning of like, man, I really needed to ask something, but he ended class way too early? I mean, we ended late, but was there anything left over? I know now I'm asking you to think back before the weekend. Yeah.
This is just one continuous project, right? Each submission is just like like the check-in on the progress for it, or is it like separate projects groups? I assume it's just one continuous project.
So the next 3 projects that we do are going to be like actual Jupyter notebooks, and it's just stuff that I think is interesting and nice applications for dynamics. And then we'll come back to your project in module 5.
Okay.
So we're kind of, the main thing is that I want you to have like something that you're thinking about now. It's like a guiding, like, all right, if I understand this, I can do something. Like, I'll understand guitars, or I'll understand cars, or something like airplanes, rockets, Pokemon. I don't know. It's like something that it's like, all right, this class is important because X. And then as we do these other projects, hopefully you can see like, all right, I can change this and connect it this way, or no, this isn't going to help me in my like ultimate goal. So more like hero's journey approach. We'll do a lot of the wax on, wax off, and then you go in with the crane kick for the win. Other questions about Friday or end of the semester stuff, like building up to it? Forging ahead? Cool. So then after that, we're working on homework 2 now, so jumping into module 2. Yeah, module 2. And module 2 is a lot of like thinking about motion. So we're going to do some problems that are called like inverse dynamic problems. That's when I know I want this thing to move in a certain way. So let's assume that it does that, and then figure out what forces I need to create that motion. That's called inverse dynamics. And then we'll do other stuff that are more like kinematic problems of like, all right, what constraints do I have here? How does that affect like total motion of our system? Sound like a plan? And problem one is jumping right into a flywheel. So we have these two forces, kind of like ripcords, that are yanking this thing. And this is that inverse dynamic problem where I know I want the thing to rotate at 50, really it's radian per second squared. So I know how fast I want it to rotate, and I want to figure out how much force it takes to do that. So I know how the forces are applied, so how big do they need to be? Yeah, this is really, I don't know why it deleted that 1/2 squared there, but per second squared. So where do we get started? What are we doing first? Free body diagram, everybody's favorite, right? Start with our free body diagram. Cool. What does that look like? We'll get started there. Yeah, because if we say that it's a point mass, then if you apply any torque, it'll. Well, if you apply a torque on a point mass, really it'll accelerate infinitely. Yeah. So it's gotta have some kind of rotational inertia. Yeah, so like that little white dot is some kind of
Which question did I get? Which one was it, Brayden?
Oh. So let's start with like because I think some people are kind of stuck, not expecting, we're doing this together because I expected to like try to help each other through it. What is moment of inertia? Have you heard that term before? Heard it? Yeah. Resistance to motion. What kind of motion is it resisting? Which one? Angular? Yeah. Angular motion. Yeah, so roughly, at least this is the way that I kind of think about it, is like my mass is describing the center, like the very center of, I think for man it's somewhere like around here, but it's like the center of me and it has some magnitude, like that's how much mass I have. My moment of inertia is describing how spread out that is, almost like what am I thinking of? Like the mean and the standard deviation. So like my moment of inertia is sort of standard deviation of my mass. So it's describing how hard it is to spin and why it's so difficult for a cartwheel, doing a cartwheel and rolling down a hill and all that fun stuff. So moment of inertia is like resistance to angular my resistance to angular acceleration. Let's starting with that. Just kind of identifying some stuff that's going on. In the first module, a lot of the free body diagrams we drew had moment of inertia equals 0. What was that? When did we say I equals 0? We did it a few times. We didn't actually say, I'm assuming moment of inertia is 0 in this case, but
when it's not spinning at all.
we could say when it's not spinning, yeah. Then it might have a non-zero moment of inertia, but our alpha, like how much its angular acceleration, maybe we assume that was 0. So that would be one case where there is no change in angular momentum. Yeah. Yeah, so a point mass is going to be, like, no matter what orientation it goes into and no matter how fast it spins, there was no torque applied. That's a point mass assumption, is that I is 0. And that's the main difference between point mass and rigid body. Yeah. That one's radian per second squared. Yeah, not just radians. Yeah. Yeah. I don't know why I dropped my second squared. Oh, you coming? There we go. Oh my God. Something's making my computer like jump around. Oh, I didn't plug it in, that's why. Critically low battery. That's not going to help anybody. Any better? Maybe. So really, like, the flywheel has some kind of support. Have you heard of a flywheel before or seen one? Something? It's a way of storing like mechanical energy somehow. We use them in, I say we as engineers, the royal, like, people that design things use flywheels almost like a mechanical capacitor. Like, things are spinning and I need them to keep spinning even if I'm not providing power. So combustion engines use flywheels. One thing you could do is like use a flywheel to store electrical energy, because you pump electricity into an electric motor, it starts spinning. If you have low resistance, now you have lots of rotational kinetic energy, and whenever you need it back, instead of using the electric engine, you use the engine as a generator, and it gives you that electricity back. Can't store a lot of energy, but you could store some. But anyway, that's our flywheel. So we've got a force here, and we've got a force there. Anything else? We talked about friction. Hopefully friction's low for a good flywheel, but could be there if you wanted to say that it's there. Anything else? No? If I say, so this is one thing that we're kind of getting into now. If I say it has to rotate around a point, there have to be forces forcing it to stay at that point. They don't have to be large forces. They could be basically 0, but technically they're there. So really, I'm saying it can't move left or right or up and down. So let's put in Rx, Ry and say, no matter what, no matter how poorly I yank on those things, it's not going to move anywhere. Like even if it's at a crazy angle. That's like when you start your lawnmower, or lately it's the snowblower. Start the snowblower. When you pull it, the snowblower doesn't come with you, hopefully, and that's what those reaction forces are. No matter how big of a force I pull on it, it always stays put. So then we end up with three equations, same as like statics, right? Sum of the force is x, sum of the force is y, sum of the moments. So let's just look at the forces to start, then we'll figure out what to do with the motion after. Sound like a plan? So we're just looking at the kinetic side, what's causing the motion, then we'll figure out kinematics, what's going on. At least that's how I want to do it. If you want to go about it a different way, that's okay. We'll catch up. We'll catch up to you. Mechanics 1 does modes of variables instead of modes of inertia. right, so I saw, seemed like forces were good. We're saying we got a positive F minus an F, and then plus that Rx if we want. And then we have Ry. This one, I saw a few different ways of doing this. I saw R times F plus R times F. I saw R times F minus R times F, and negative RF, negative RF. What do we think? 1, 2, or 3? For the sum of the moments. Just talking about like that, and here like Rx and Ry 0 moment, right? Because they're being applied right at the center of the object, so not applying a moment. Yeah.
It would be 3.
Number 3.
Two forces are inducing clockwise rotations and negative.
Yeah. So if we're using like right-hand rule, the two forces are twisting the thing into the page. That's how, when I'm like upside down working on my bike, I use the, like if I want to tighten something, I do this, make sure my right hand is going to tighten the screw. If I want to loosen it, turn it this way, make sure that I loosen the screw. So right hand rule works for like screwing into something or taking it out, unscrewing something. Yeah, so we got this one. So we have like negative, negative. If we want to, and so number 1, number 3, technically you're gonna get to the same answer as long as you're keeping track of those signs. I had a friend in grad school that never worried about plus or minus sign, and his hope was just that he was gonna make an even number of an odd number of mistakes, so that sooner or later it works out. You always end up multiplying by one or the other, so sooner or later you'll make a mistake, so why not just always make the mistake and just hope for an odd number? And he was right half the time. Half the time, it works every time. All right, so now we've got, all right, yeah, we'll leave it up here. Oh my God, give me back my pen. What are the sum of the forces in the x direction equal to? What's the total sum of forces? 0. AX is 0, MAX is 0, so total force has to be 0. So that first equation tells us that Rx is 0, that there is no reaction force. I mean, it's there, but it's just not applying any force. Yeah?
I have a question with the alpha term. So if we're saying that like with the total force being minus negative, then how is the alpha term also negative? So it comes correct.
So what we're saying is, oh, sorry, Tina, I missed it. Is that it's going to rotate in a negative direction, and we're applying a negative moment. So we'll have a negative and a negative, when we can cancel that out and say that torque equals I alpha, instead of like a negative moment equals a negative I alpha. Yeah.
I think the reason why it's negative is the picture has alpha going the other way.
Yeah, exactly. So I'm trying to maintain like a consistency of like to the right is positive, up is positive. If that's the case, then the cross product is going to be out of the page is positive. So z-axis spin is spinning counterclockwise. Now, maintaining that right hand rule. And yeah, I guess that's a good segue. Like angular angular velocity and moment, those are vectors. So they have a magnitude, and the direction that they're pointing is describing the axis of spin. So what axis is it spinning around? So in this case, everything is along that k-axis. It's either counterclockwise or clockwise, because it's all like a two-dimensional problem. So rotation happens out of plane. All right, so sum of the forces x is 0, sum of the y is 0. What is our sum of the moments? I alpha, yep. I alpha, like that. No further explanation. I'm pausing to see. Does that seem like it may? Are you like, that's exactly what I would have done? Or, geez, I better write this down because I've never seen that before in my life. One or two, halfway, somewhere. All right, so quick aside. Quick side note, sum of the forces is like the change in MV. It is MA, right? If I say the sum of the moments, really it's like R cross, kind of resultant R cross, that sum of the forces is R cross ddt of mv. And a little bit of magic, but the thing that comes out of this is that the sum of the moments, which is R cross F, is like ddt of R cross mv. So based on, if I have sum of the forces is ma, so change in momentum, sum of the moments is a change in angular momentum. And changes, and angular momentum is always like I times rotation rate. Like, so if I have so much angular momentum and I'm rotating, I've got so much angular momentum. But that's just like a quick, if you're like, I'm not going to do the readings, I'll just learn it all in class. That was your quick, like, 3 pages worth of readings. That's what you need to know. So negative 2RF equals I alpha, right? Now we have one equation, one unknown. So we know how fast we're spinning up, and we know what R is, we know what I is, so we're just solving for F. I'll just check in as people are kind of doing the math. Yeah, so like theta dot. You know, so yeah, it's like d theta dt. Yeah. Yeah, like sometimes it goes theta, omega, alpha. like that. Yep.
I was done by day 2. I'm scared. See, but I've never been. I don't really care that much. Have you ever seen a study for exams? They're like setting up a day where we're all like just gotta watch you. I think it's in my just an announcement that they're dependent on the weather, so it might not have to begin. What classes did you exam? Yes, it's just Bro, you gotta start training this week.
Yeah, you guys could.
And I'm tuning out for people that are so what?
All right, cool. And what do we have? 0.5. So kind of like this, like plugging in. Oh yeah, let me put the units back in there. And then shouldn't that -50 and the -2 both cancel out? And like 125 kilogram meter per second squared. Do the units work out? Shouldn't the force be a Newton? Why does it have mass and acceleration in there? What? Yeah, what happened to the radians? Don't we have like a times a radian? How are these units working out? Does anyone know units of a radian? What is 1 radian? Yeah.
It's degrees, right? So, or like kind of degrees, so it's like dimensionless.
It is so degrees are not dimensionless, but radians are dimensionless. Yeah. So a radian is a meter per meter because it's describing like circumference and diameter, like how they're related. So it's a meter per meter. So so the radians, anytime you have a radian in your unit, it disappears. Like it's not actually part of the unit. So that's a nice part about radians. Different from cycles or degrees, those have like actual units in them, so we can't use those. All right, so that one's good. What about the kilogram, meters? Where are my newtons? It is a newton. All right, thank you. Yeah, nice. 125 newtons. Cool. Always good to check your units. Double check. How are we doing? What do we want to do? If we start a whole new problem, we're not going to get through it, right? Take a mental break and just collect ourselves before the next endeavor. All right, let's call it. We have a number. We got a number. Like we finished a problem, and we'll stop there. Thanks for coming on this journey. We'll stop. We'll meet up on Wednesday.